Thank you. So a pleasure to be here, and thanks for the nice introduction. I'm indeed passionate about functional programming, so since this is a development track, I thought I'll tell a bit about this. So what is it? Functional programming as such has been around for years, 30 or 40, depending on how you count. But there's been some recent change. So if you look at areas like maybe fintech or data mining or maybe even blockchain, there is a community of young, angry people around there, men and women alike, that do think functional programming is the coolest thing to do in these areas, which on one hand involve clever algorithmics, where the algorithms are tricky and hard to get right. And also, you want to do things on the large scale. You want to care about maintainability. You want to care about readability of what you've written. So I'll tell you a few things about functional programming is about, and then I'll give you a few pointers where to look. And since this is a short talk, of course, I cannot get very far. First, I want to take you a long time back. I think this is one of the world's oldest algorithms ever written down. And the strangest thing is, this is one of the most advanced ones because it runs on infinite data and takes infinite time to run, but still is a very useful one. So it was formulated by Eratosthenes in ancient Greece. And he was interested in prime numbers. He just wanted to list, numbers like 2, 3, 5, etc., numbers that don't have any other factors than 1 and the number itself. And he formulated this algorithm in this crazy way. He says, well, you start off by writing out all numbers, starting from 2. 2, 3, 4, 5, 6, 7, 8. Already that should take a long time because there are infinitely many numbers. So you're stuck on the first step. But then he goes on. He says, next you should do the following thing. Repeatedly, put the first number aside and remove its multiples from the rest. Yeah? You should go through this infinite sequence of numbers, do some action, and then you should repeat this activity ad infinitum, infinitely many times, and then you see what you've got. And what you've got are all the prime numbers. So if you could do so, actually this thing that would happen that is on the screen, you first write down all numbers, starting from 2. Well, I haven't quite written down all numbers because this room is very limited and this slide is very limited, but in principle you could do it if you had all the time of the world. So then I set aside the first number and I remove all of its multiples. So I remove 4, 6, 8, etc. And this is the second line here. And it also takes, an infinite amount of space and should also take infinitely much time. Then I set aside the next number that is left, 3, and remove all of its multiples, 6, 9, 12, etc. Well, 6 was already removed, but 9 wasn't. Then I have 5 as the next guy left. I put it aside and remove all its multiples. Well, and 10 and 15 had been moved from here already. But for example, had we seen a bit more, 25 would have not. And this is the stage where we remove it. And then here's infinitely many more steps, each of them taking infinitely much time. And once you've done with all of this, which will take you a while, you have all the prime numbers. So that's a perfect algorithm. But it's kind of idealistic. And it explains very well what prime numbers are about, but you can't really write it down, can you? Well, the point is you can. So there is this functional programming language, Haskell, that will actually work with infinite data structures for you, and you can literally write down what the Greek guy had taught you to do. So all you say is, you define the sequence of natural numbers from any number. From of n is just the number n, and then you repeat from n plus 1. So you put down 2, and then from of 3 gives you all numbers. This should take infinitely much time, but it doesn't, as we will see. And then you sieve what you've got. So what you do, you put the first number aside, you prune the rest, which is ns, from all the multiples of the first number, which is n, and then you apply sieve to it again. And here is just a thing that checks whether n is a multiple of k, and here is a small thing from pruning, multiples of n, multiples of k from the sequence ns. You just filter the infinite sequence by leaving out the appropriate thing. And then the sequence of prime numbers is nothing else than sieve applied to from 2. And you can run it, and you get out exactly this thing. We'll keep printing on forever if you don't stop it. Should this not be impossible? So that's the story. I'll tell you briefly what functional programming is, what are some functional languages, what makes functional programming appealing, and what is the applicability of this paradigm. Okay, functional programming, what is it? Well, the first functional should perhaps just mean that it works, right? I mean, it's functional. And it does mean that is a good pun to have. The word could mean it works, but actually it means a bit more. Technically, it means you only program functions, or maybe you almost only program functions. So whatever you write down in your functional code would be functions, and functions in the old school mathematical sense. You know, things that transform arguments to result values, or inputs to outputs, if you wish. You know, squaring is a function. It takes 3 and gives you back 9, or takes 4 and gives you back 16. And you only write down these things. Now, this looks like a good exercise for a math class, but can you program with it? Because programming should be so much more. It should be about the web. It should be about apps. It should be about interaction of the user and the system. How is it that these are only functions? Well, it all depends on your viewpoint or the kind of glasses that you put on. So while it's true that if you look at functions naively, you cannot do so much with them, and you have to add quite a bit to actually get going, but there is this paradigm called purely functional programming, which is really radical. It basically is this slogan: even if you've got a thing that doesn't seem to be a function at all, you're foolhardy. You say, it still is a function. Just insist on finding a way to look at it properly. And then once you've found a way to look at it as a function, you actually can program it as such. And it might look like a very bad idea to do, but wise people have done this, clever, witty people, and it works miracles. So here's some examples. So maybe your simplest thing, your function isn't quite the function, because maybe the computation you want to encapsulate in it would sometimes raise an exception and not the value. Yeah, then it's not properly a function, because not for every input you do get an output. But you say it's a function nonetheless, because what it returns to is a data structure, is a choice of what you want it to get, or possibly a failure. This is a small little data structure. Indicates whether you succeeded or not, and if you did, gives you a value. If you've got an interactive input-output computation, it doesn't look like anything like batch mode computation, taking one single input now to an output later, because it should be about interaction. But a good way to see it is you have some initial state, and what you produce is a potentially infinite tree of a dialogue between the user or the, the consumer of the system and the system itself. And then actually, what you're programming is a function that returns this dialog tree. And while this is as infinite as this sequence of prime numbers, you can work with this infinite data structure in finite time. And the trick is, you do it in a lazy manner. You never actually touch any part of it before ultimate need presses you. So it's all using, the weaknesses and strongnesses of the human nature, and the prime one is lazy. Never do anything until the last moment. I did this with my slides, and the organizer was not happy. But here I am. So functional programming comes from this utterly simple calculus that was invented by a logician, Alonzo Church, in the 30s. And as such, it has very little ingredients. All you can write down is expressions. They stand for functions. And in these expressions, you can have variables here and there. One thing you can do is you say, now I've got an expression, maybe it's called t. Let me tell you this expression is a function in x. You abstract out x. This is called lambdas. And then once something is a function, you can apply it to another function. So you can supply one thing as an argument to another. And there is nothing else there. Well, it doesn't quite look like the prime number program that I showed to you, but under the hood is nothing more than that. It's literally these small ingredients plus a lot of sort of syntactic sugar goodies for making it practical. And there is only one computation mechanism in this paradigm which says if you've got a function given by an expression in which you've said x is the formal parameter, then you can apply such a function to an argument, and all that happens is this expression t is kept, and everywhere throughout you replace the formal parameter by the actual argument you care about. One adds a little more to functional programming, usually to make it useful, and this is, you say everything you program is function, moreover, it is typed. By typing, I mean, you know what inputs or arguments you care about, and you know what, what outputs or return values you care about. So you're very specific about the domain and the range of your function. And basically, you promise, I'm only going to work on arguments of a suitable type, and I promise you, that is consuming my function, that I deliver values of the given output type. So everything you write down is typed. It doesn't have to be typed by you. It can be typed by the language processor. So depending on if you've written down the type for your function, or if the language processor does it, different things may happen. So if you write down the thing, the machine is going to check it for you and tell you if you are good. If you don't write it down, the machine will infer the type for you, and it will tell you you wrote complete nonsense if inferring the type fails. So this process of type checking or inference, depending on whether you wrote the type or the language processor inferred it, actually guarantees programs don't go wrong execution time. So it's never possible that you get a message not understood or a wrong argument error. But there is more to it, because this discipline of typing, programmer-provided types, they also serve as a kind of documentation. You've written down what you intended, and this is good for you, it's good for your pals. And the machine-inferred types, well, they are not there as a documentation. You could add them later, but they kind of serve as a confirmation that indeed the machine understood what you meant and you didn't make a mistake while you wrote it down. If you have types, then there is a way to complete the lambda calculus so the types are around, and Church also did that. He said, well, we've got these expressions, T, they are typed. Any expression must come up with a type. The type could be a capital A. Among the types, there are these function types, A arrows B. There are some base types, like your number types and string types, etc. And there is only two typing rules. You have to make sure that your lambdas are good, and you have to make sure that your applications are good. When does a lambda have a type A to B? It takes A's to B's. Well, if in the context where you can assign X a type A, T will come out as having type B. Typing of applications, if you have applied T to U, this is only possible if T is a function taking A's to B's, and then U must be an A, and what comes out is a B. And this mechanism of computation reduction, this actually preserves an expression's type. The first functional language was invented way ago. So that's would be 60 years, isn't it? So Lisp was developed at MIT, AI lab for AI applications. And maybe not in its original form, but its successors are still in use. And it's remarkable that Lisp is the second oldest high-level programming language whose dialect is still in use today. So another one as old or a bit older than would be Fortran, that exists in high-performance computing still as a niche language. So Lisp is maybe not an ideal language of mine. It isn't purely functional in the sense I explained. It isn't typed either, so it's both impure and untyped. And there's a very crazy syntax where all you can see is lots of parentheses that are kind of unnecessary, but this was This was the taste of the people that developed Lisp, and it is still the prevalent taste in the Lisp community. But apart from Lisp, there is a whole zoo of functional programming languages. There are those ones that we tend to call the Lisp family. It was developed into Scheme, then Common Lisp. Closure is a recent one, which is maybe 5 years old. Typed languages started with ML around the 70s already, but they were standardized and became really programmers' tools in year 1990. So that's the date of both standard ML, Clean, and Haskell. And these days, perhaps, the most used typed languages of this, these two families would be OCaml, which is a French thing, stands for Objective-Caml, F#, which is a Microsoft language compatible with .NET and compiling to the CLR, and Haskell. And then there is more. There is Scala, which is a combination of functional and object-oriented languages. There is Erlang, the Ericsson original thing, specifically from concurrency. There is PureScript now for scripting. There is Elm for user interfaces. There are these languages that push type systems to the extreme. Examples of those are Agda and Idris, which are dependently typed. In a language like this, you can write down very precise specifications of your program in the type. What makes these things to work? I pointed out a few details here. So most of these languages, apart from the Lisp family, they are typed. So types help a lot. I'll try to explain why. And then I've also marked some languages as eager, some as lazy. Laziness is one of the big things you can have in functional programming. And where it helps in particular is this programming with data structures that are sort of morally infinite, but you do want to implement them in a finite way. Like this sieve of prime numbers, of course you only ever care about some initial segment of prime numbers, but it's useful to think of it as an infinite sequence, and then you don't have to care about, which initial fragment you're actually working with, and, have I done enough filtering? None of these things need to be there. So these are called lazy. The languages where you cannot have this are called eager. In an eager language, you really have to fully evaluate the argument before you supply it to the evaluated function. In a lazy language, this is not the case. You start applying the evaluated function to the argument, and you only ever evaluate the argument if a need for this arises, and then also only once, and that helps. So what is the spirit of FP? Apart from this mentality that everything is a function, there is one big idea, which is abstraction, and that goes towards modularity and compositionality and reuse and easy to understand. And it's the principle, if some phenomenon, or sorry, in your particular code, if some kind of thing recurs a lot, maybe not literally, but in some variation, you do abstract it. And functions are an example of this. You see that you're doing the same activity multiple times around in your program, then of course you do write a function or a procedure or a method for it, not to write down the code n times. But you take the principle to the extreme. Whenever you've got something that you can abstract over, you do abstract. And this leads to much more modular code that is easier to understand. And the caveat is, or not. If you just go over the top, then there are limits to this. And then, as a language designer, you try to choose, you try to create languages that abstract those kinds of recurring things that programmers do care about. So it's not only about making functions, it's about making so many more things. I'll give you some examples. So one big thing that you have in functional languages is functions may take function arguments. And another thing is functions can be defined, sometimes functions can be defined for every type. And then it should be implemented in such a way that the implementation is not specific to the type of the argument. Here are the two ones that I used in the Civ program. So somewhere, I'm sorry again. Somewhere there was this filter function for removing multiples from an infinite sequence of a number. And it's based on the idea of sending a sequence to a sequence based on another function, which takes a number and tests whether it has a given property, here whether it's a multiple. So this filter thing takes in two arguments. One is your sequence, but the other is function that you use for checking. I also combined the check for being a multiple and negation of a check. And composition of two functions is a completely generic thing. You can always get a function from A to C if you've got a function from B to C and A to B. And this works irrespective of the type. A, B, and C on this slide are type variables. So signifying that it doesn't matter which types we're talking about. A, B, and C could be any concrete type. Another big abstraction thing you do is, well, sometimes similar functionality is shared between different types, but cannot be implemented in exactly the same way. So function composition is the same no matter, you know, what the domains and ranges of your functions are. But for example, if you want to do summation, or if you want to do equality check, or if you want to be able to print out values of a particular data type, this is implemented differently for every type. But still, printing something is a functionality shared between many types. So then what you do is you collect together types or type constructors that share similar functionality. And in that program, two were used. Show was implicit, but it was there where I showed you the infinite sequence or the beginning of it that is printed out, that actually implicitly uses show. So this is a type class collecting together all these types whose values you're able to print. And sequences are one such thing. And then there was also, there was integer division. There was modulus somewhere in the code. And that is not characteristic only of the integer type, but any integral types. You actually use a very specific type class to hide away this thing, which I said, not everything you can easily see as a function. These things that you cannot see so easily as functions, you typically put away in a type class called monad. And here is a pun. This is a T-shirt worn by many in FP conferences. The concept of a monad comes from category theory, but it becomes, which is deep mathematics, but it's very useful for modeling impurities in functional languages. There is more abstractions, and I don't want to go into them. But in languages like this, you've got user-defined recursive data and record types, and then you can do generic programming over the constructors of these types. You can do type-level programming, which means you can write functions that send types to types. So it's like going one level up. You can do dependent types, which are types indexed by values of other types, and they allow for a very precise way of specifying function domains and ranges. And then finally, in half of these languages, you have this idea of laziness, which says, really, the argument in an application of a function to an argument is only evaluated when you already started to applying the evaluated function to it, and then only when you actually need that argument. And the consequence is, when you have a data structure, be it finite or sort of idealized infinite, only as much of it is ever produced by a given point of time as much is consumed by that point. And this enables you programming with infinite data structures for free, so you don't have to think about it. So for example, this program from that we had that generates the sequence of numbers starting from n, when I apply the function take 5 first elements from it, it will not generate more than 5 elements because it's computed in a demand-driven way. I start taking 5 elements of a sequence that I do not have yet. And at the moment when I take the first, I create the first. At the moment when I take the second, I create the second. When I've gotten all my 5 elements, I don't care about producing the 6th anymore, and I don't compute it ever. So some strengths of FP, summarized on one slide. This allows you to program in a high-level declarative style, which is meant to be easy to develop and understand. You can write very difficult programs very short. You've got safety from strong typing. This idea of abstraction, abstracting out anything that recurs, helps tame complexity. The idea of purity makes programs amenable to automatic and semi-automatic analysis and reasoning about programs. So you can have resource control, you can have time complexity control via static analysis applied to functional programs. It is especially well suited for mathematical domains. So that would, for example, be the case in fintech. or maybe also machine learning. It's very well suited for manipulating of linguistic data or any data conforming to complex data schemes. So particularly suitable for implementing other languages, metaprogramming, DSL development. There are some weaknesses. They come in two categories. There are the perceived weaknesses, or the kind of prejudices against functional programming, and there are some real issues. So the perceived ones are poor performance. This might have been the case some decades ago, but these days it really only applies to domains where very direct low-level programming of resources is desirable. I don't know, if you're programming network protocols, you have to think about these things. If you're doing certain paradigms of parallelism, you have to be careful, but otherwise, performance is not an issue. Also, there is this feeling among some people that purity and strong typing limit expressiveness, but this is just plain wrong. It really depends on if you've gotten the idea of the paradigm and it is not limiting expressiveness. There are some real issues, which is programming education is not geared for functional programming traditionally, so there is not enough programmers around on the market. In some cases, FP languages are developed by small communities, which then has the result that the support, especially longevity support, is weak. Applications in the real world, numerical computing with complex algorithms like fintech, like machine learning, big data, working with rich data, web, concurrent and parallel programming. There are very nice abstractions to actually tame the complexity in concurrent programming. And also security, critical, and correctness, which maybe is relevant for blockchains. So these days you see so many blockchain companies advertising and they want to employ functional programmers. So there are some books that advertise real-world applications of functional programming in all major current bigger functional programming languages like Haskell, OCaml, F#. And apart from serious applications, there is also entertainment ones. So there is a very nice workshop on functional art and music that is held every year. So FP is also perfect, for example, in applications to music, because it's mathematical in nature. You can really code up harmony and polyphony rules. You can do automatic harmonization, automatic composition. You can do functional art modeling and design. And I want to finish off actually by this beautiful scarf. So there is a startup in the States by Fabienne Serrier. She is producing scarves and has bought knitting machines. And every scarf is unique. And this one here is just the printout of a behavior of a cellular automaton. I think it's Conway's Game of Life. So you can do really cool things with functional programming. Thank you.